The Cosmic Origins Spectrograph, COS, is one of the most advanced ultraviolet instruments ever installed on the Hubble Space Telescope, and its value comes from what it measures rather than what it images. COS is not designed to take pictures. Instead, it separates incoming light into precise wavelengths, producing spectra that reveal the physical properties of distant cosmic material. Every element and ion absorbs or emits light at specific wavelengths, and these signatures act as fingerprints. By analyzing them, astronomers can determine what distant gas is made of, how hot it is, how fast it moves, and what physical processes are shaping it. Without this kind of spectroscopy, our understanding of the universe would be largely superficial. COS specializes in ultraviolet UV wavelengths, a part of the spectrum blocked by Earth's atmosphere. Ground-based telescopes cannot detect this radiation, so the instrument must operate from space. UV light is especially important because hydrogen, the most abundant element in the universe, has its key spectral features in the ultraviolet. Since hydrogen is the main tracer of normal matter on the largest scales, UV spectroscopy is crucial for mapping how matter is distributed throughout the universe. One of COS's core contributions is the study of the cosmic web, the immense network of filaments, clusters, and voids that defines the large-scale structure of the universe. This web formed over billions of years as gravity and dark matter pulled gas into elongated structures. Most of the cosmic web cannot be photographed directly because the gas is far too faint. Instead, astronomers observe how the gas absorbs ultraviolet light from bright background sources like quasars. When quasar light passes through diffuse hydrogen, certain wavelengths are absorbed. COS measures these absorption lines with exceptional sensitivity, making it possible to detect extremely thin gas that older instruments could not observe. By collecting these measurements along many lines of sight, scientists reconstruct a three-dimensional map of the cosmic web. Understanding this structure is essential for understanding galaxies. Galaxies form inside filaments of the cosmic web and depend on a continuous supply of gas to form stars. COS reveals how much gas is flowing into and out of galaxies, how enriched that gas is with heavy elements, and how its temperature and density vary. These details determine whether a galaxy forms stars actively, slows down, or becomes quenched. In other words, COS helps explain why galaxies evolve differently and why some remain star-forming while others fade. Another major achievement of COS is its role in solving the missing baryon problem. For years, scientists knew that the amount of ordinary matter observed in stars and galaxies did not match theoretical predictions. A significant portion of expected normal matter was unaccounted for. COS observations show that much of this missing matter exists in warm, diffuse gas in the halos surrounding galaxies. These halos extend far beyond the visible parts of galaxies and contain more mass than previously recognized. Surveys using COS, such as COS halos, demonstrated that these gaseous envelopes are central to galaxy evolution and serve as reservoirs of material for future star formation. One of COS's core contributions is the study of the cold interstellar medium, the gas from which stars and planetary systems eventually form. By detecting ultraviolet signatures of elements like carbon, oxygen, silicon, and magnesium, COS helps astronomers determine how many generations of stars have enriched a region. These chemical abundances reveal the star formation history of a galaxy and its level of chemical evolution. Installed during Hubble's final servicing mission in 2009, COS was built for sensitivity rather than general versatility. It focuses on faint ultraviolet signals that other instruments are unable to capture. Since its installation, it has generated results that significantly altered our understanding of galaxy growth, intergalactic gas, and the exchange of matter between galaxies and their environments. Large research programs built around COS data have shown that galaxies are not isolated systems. Instead, they constantly interact with the gas around them. Supernovae and black holes drive gas outward, while gravitational forces pull fresh gas in. COS measurements quantify these flows, offering clear evidence that the space around galaxies is an active, dynamic region rather than empty vacuum.